this time you notice the quizzes are all based on the homework. Now for today, did anybody have any questions about any of the homeworks or anything like that? All right, by the way, are the quiz solutions available? Are those on one up now?
This one is. The first one is.
The second one's not there? I'll put it up.
Yeah, second one's not.
Send me a note and I'll put it up right after class. All right. What's that?
I don't know how to send you notes.
My email.
Oh. I thought you were like on OneNote.
No, I don't know how to do that. Yep.
I've got a question on it's s squared minus s plus 1 over quantity s plus 1 squared.
And you want the inverse?
The inverse.
All right. Let me get to that, but I want to do one thing before this. All right? And I'm trying to set this up. Last time I did something, and I looked at the video, and I felt stupid I did it, but I'm just going to make sure this proof is correct. Give me a second. Did anybody look at that video at all? This weekend, I guess not. But if you look at the videos, if you ever get a chance to do this, what I'm doing or something like it, always have people record what you say. That way you can go back and see if you made an error. A lot of times you're oblivious if you don't have a recording of it. Now, nobody said anything, but when I was doing it, I was thinking, I'm leaving out something here, and then it dawned on me. All right, this has to do with how to calculate the Laplace transform of the time derivative of x. Let me go through this. I said d of uv is equal to u dv plus v du. Now, you don't have to write this down. I'm just doing this to make sure, for the record, let's say that. All right, now when I have this, when you integrate this, you get uv. Integrate this, you get u dv. Integrate this, it's v du, all integrated, right? Now, what I said is when I had the x dt, and I wanted the Laplace transform of that, that is the definition of the Laplace transform of the derivative of x with respect to t. Does everybody agree with that? Now, here, I make dv equal to dx dt, and therefore v is just x of t, and I make u equal to e to the minus st, and therefore du is equal to minus s e to the minus st dt. I'm just doing this for completeness. Now, this is a udv integration right here. It's like udv, so if I want to solve that, I would take this to the other side, have minus the integral of v du, and it would be plus the integral of that. Correct, class? Just for completeness. Does everybody follow me what I'm trying to do here? I'm trying to use the exact format that I had up there. I'm taking dv or v du to this side, so there has to be a minus sign, but they're integrations. I didn't put the integration part up. That's the reason I'm saying this. I don't know if you caught that. Probably a lot of you did. So when I do this one, now I'm going to get the differential of uv integrated. Well, u times v is just going to be x of t, right? It's the differential, actually, yes. The differential of x of t times e to the minus st integrated from 0 to infinity, which is just going to be x of t e to the minus st. And then it's going to be minus the integral of v du. Well, v is x of t here, and du is minus s, makes that plus, and I can take the s out in front, e to the minus st dt from 0 to infinity. You follow me? The only thing I'm doing now is casting this in terms of a udv integration. This is what I did last time. I didn't put the integration down. Follow me? When you integrate this, you see that this, in fact, is the definition of the Laplace transform. This becomes x of s. Do you all agree with me? And this here, when you integrate that, you get x e to the minus st, don't you, class? Right? When you evaluate this at infinity, I mean, when you integrate the differential, you get xt times e to the minus st. When you evaluate x of t times e to the minus st, when t goes to infinity, that goes away. It goes to 0. Correct, class? Then when you evaluate the lower limit, it's minus x of 0 e to the 0. Well, e to the 0 is, in fact, 1. So it's just going to be this whole thing boils down to s times x of s minus x of t equals 0. Put it 0 plus just after the event begins. You all see that? I'm sorry I messed that up last time. Are you with me, class? I didn't do the integration. That's the first thing I want to do. Second thing I want to do, since you asked me about the inverse Laplace transforms, I know you've had these, but what I'm going to do is go through several of the most common ones. We know, well, I'm going to show you how to get single poles, double poles, and then complex poles, all right? But I want to make sure you've done that. How many remember doing these, by the way? Inverse Laplace? Do you not really? You all had differential equations, right? You had to do inverse Laplace to solve most of the differential equations. Didn't you, class? Partial fractions? You had this. You may not remember it, but you will. So the first is if you have a simple pole, and I said if you had something like 1 over s plus a times s plus b. I'm going to do something different here. I'm not going to just leave this as 1. I'm going to leave this as some k times s, okay? Now, simple poles mean, first of all, pole is a function. When a function goes to infinity, it occurs at a pole. A simple pole is simply one like this. If I have 1 over s plus a, the order of the denominator is 1. The power on s is 1. Do you see that? It's s to the first power, I should say. That's a yes, sir. Oh, that's a simple pole. The pole occurs at s equals minus a. That's where this function goes to infinity. That's what a pole is, just for clarity. With me? Now, simple poles are that. Double pole would be this squared. That's a more complex pole, but it's called a double pole. Now the order on s is squared. If it was cubed, that would be a third order pole. Understand, class? The order on s squared. And we can get into complex poles and stuff like this. But anyway, when we do this one, just so everybody knows it, this is always going to be something where we do it something is we take this and make fractions of each pole. That's the idea with simple poles. For this one, you're going to have some unknown constant a over s plus a plus some unknown constant b over s plus b. Understand? Now, I'm going to tell you this. If the order here was like s squared plus as plus b, then there would have to be an as plus b there. The order of the top part would have to be 1 less than the order, when I say order, it's the power on s, would be 1 less than the actual denominator if it would be a complex pole or a higher order pole. Understand? How many remember this? Let's go through this. So how do I get a? Well, to get a, I've mentioned this, we multiply everything by s plus a, both sides, right? Gets rid of the s plus a on that side, puts an s plus a there, gets rid of the s plus a there. Then we allow s to go to the pole, which is minus a. So to get a, you really take this function. Let me just call this x of s. I take x of s, and then I multiply it by the pole, which is going to be s plus a. And then I say as the limit, as s goes to minus a, that will be the value of capital A. Do you all agree with that? How many do? I'll put numbers in to make it more clear, but I have to go through this. I didn't go through this simply with you, and I was sensing that some people really didn't know what was going on. That's the reason I'm doing it. I thought everybody did, but how do I get B? It's really the same thing. The limit as s goes to minus b, right? Of x of s times s plus b. Correct, class? Now, the reality of what I'm doing there is I'm simply, if I want a, I simply cover this up. And I evaluate with what's left at s equals minus a. Follow me? Everybody? That's the reality of what I'm doing. Then if I want b, I cover up the pole of the s plus b here, which is the pole at where s goes to b here. And then I just evaluate the remainder at minus a. Understand? Simply, right? Everybody? We'll do an example, but I wanted to make sure I said that. So, to continue, I'll get to you, but I want to make sure we see this first. By the way, any update on the weather for tomorrow?
No.
They said they don't expect any severe weather here specifically.
Now, I saw an Auburn alert thing that said they don't expect snow here, but I've heard that before. What? I mean, I'm serious about this. I have been here when they said, no chance of snow, like 2 days earlier. And then there's 3 inches of snow in a week. So the weatherman doesn't always hit it perfect. Sometimes he misses. I'm hoping it doesn't snow, but part of me wants it to snow, just because I haven't seen snow in forever. Anyway, now for a hardcore example. Suppose I have 12s over s plus 2, s plus 4. All right? And if we want we're going to do the whole thing on this. Somehow this is the resulting, this is my final answer, this is x of s, and I want to find out what x of t is. That's my goal. So I'm trying to find x of t, but that's what I got to work with, right? I got 2 simple poles downstairs. Agree, class? So now I go ahead and I expand it. A over s plus 2 plus b over s plus 4. All right. Take a look at this. Do it yourself right now. What is A? Well, what's the pole? S equals minus 2. Cover this up. Evaluate what's left at minus 2. Minus 2 plus 4 is 2, right? So that's 2 downstairs. Minus 2 times 12 is minus 24, or minus 12. How many see that? Agree? Do you all see it right over here or not? You see it? I mean, I'm sorry, I'm blocking you. Yell at me to get out of the way if I'm blocking. You see it? No.
How bad would you do it again? Like the cover up thing?
Yeah, all you got to do is the s plus 2 is the pole, right? Cover up s plus 2 over here in the actual function. That's like multiplying by s plus 2. Then evaluate what's left at the pole at minus 2. So I got minus 2 plus 4 is minus 2, right? And then I have minus 2 times 12 is minus 24. Minus 24 over 2 is minus 12. Agree? Yell at me to get out of your way, because I don't always remember. So this is minus 12. Now I'm going to tell you a trick about this. Almost always, this one is going to be plus 12. And I'll tell you why. Because, no, I just take it back. And this one, it's not going to be. If this was a constant, it would be. If that was a constant. But because of that s, it won't be. I'm sorry about that. These are just things you see. Sorry, I put an s there for a reason. I knew it. Now, to get b, what do I do? Now I'm going to cover up s plus 4 and evaluate everything at minus 4. So what do we get? We get minus 2 downstairs, don't we? Right here. It would be minus 2 here, correct? And then we got what? Minus 48 or minus 24. Do you agree with that, class? I mean, plus 24, right? Plus 24, class? How many agree? Plus 24? Sorry. If this was a constant, if this was just 12, they would be the same value, opposite signs. Just telling you that. That's from experience. They're different now because there's an s there. Now, to get the inverse on this, and these are ones you must know, the inverse transform of these two, they're both the same general form. The first one, you just take the minus 12 and put that as a coefficient, right? And then what is 1 over s plus 2? This you have to know. Say it again. E to the minus 2t u of t. So it's e to the minus 2t u of t plus the 24 comes down right here. It's just a scalar operation, right? A constant. And then this one becomes e to the minus 4t u of t. Now, if you had to guess, or if I asked you what the value of that was just as the event began at t, just greater than 0, what would it be? Well, when t is just greater than 0, it's still like e to the 0 or 1, right? So I have plus 24 minus 12, or starts at 12, right? What's the value as t goes to infinity? Just take a look at that. This is an obvious. What's e to the minus infinity? It's going to 0, right? This particular one is called a double exponential. Well, it's not quite double exponential. It starts at a value, right? It's going to climb and then go to 0. It's basically that way. And this would be something called an overdamped pole. How many have heard that term before? Remember that? We'll talk about that later. All right, that's the first thing I want to show you. Second thing is if you have a double pole. Now this one is something you run into and you have to know this. So a double pole is something, let me give you a simple example, and I'm going to just tell you, I'll give you a number. Right? Suppose I have 12s over s plus 3 squared, pardon me, s plus 3 squared, right here, times s plus 1. Let me do it this way, times s plus 1, all right? Now, you look at that, and you see I have s plus 3 squared. That's a higher order pole. Follow me? It's squared. So the way we have to do this is we have to take the first, you have to take s plus 3, the higher order pole, but only take the first to the power 1. So it's some unknown, call it a over s plus 3. Then plus b times s plus 3 squared. What you're doing is you're going to keep repeating this term. Start with 1, power 2. If it was the third power, power 3. Follow me? Now you have to do this. Remember this. And then you put the s plus 1 plus c over s plus 1. Everybody okay with that? Now, the first, you always get the obvious one first. When I look at this, this is a simple pole. S plus 1, right? So to get the value of c, you multiply by s plus 1, or just cover this up, and evaluate the remainder at s equals minus 1. Follow me on this, class? What is that value? I got minus 12 on top, right? And then I have what? 2 down here, squared is 4, right? So I'm going to have minus 12 over 4, correct, class? Or 3. Do you agree with me, everyone? How many do?
Is it minus 3?
Well, yeah, minus 3. Do you agree with me? Minus 3. Say again? If I'm in, okay, okay. So, minus 3. Put a plus in. All right, now the next one we get is the value b of the higher order pole. With me? And the way you get it is multiply everything by s plus 3 squared. You're taking the higher order pole, multiplying both sides, which effectively gets rid of that there, right? Doesn't it? And then evaluate the remainder at the pole at s equals minus 3. And it's the cover-up method here, too, for that one. So when I cover that up, and I let s equals minus 3, what do we get? On top, we get minus 36. Do you agree with me? Mm-hmm. And on bottom, what do I get? Minus 2. Right? So minus 36 over minus 2 is 18, isn't it, class? Yes. Agree with me? So this one's 18. Now, to get the first one, A, there's 2 ways of doing it. I'm going to show you both. The way that's normally taught is that you take this function, let me get rid of this one. You're going to take that function that I've shown there. I'll write it down and show you why it works. This is called x of s. We're trying to get the inverse transform. That's our goal with all this. But now, to get a, the way you do it is you take x of s and you multiply by s plus 3, and then you take a derivative of this with respect to s and evaluate it as s goes to minus 3, and that will be a. And I'll show you why. Just write that down. This is in the book. The derivative is the product of this. Oh, I'm sorry. This is squared. That's the highest order pole. So it's the highest order pole, and it's multiplying x of s and taking derivative. Now here's how come it works. So once you see why something works, it stays with you usually. I want you to watch this. I'm going to erase this, but I'm going to show you. All right? This is in the book, but he doesn't go through these. No, I don't think he goes through these details very well. I could be wrong. So now, when I multiply both sides by s plus 3 squared, right? Follow me. Gets rid of that, right? Gets rid of that one, right? Then I multiply by s plus 3 squared, I have s plus 3 here, don't I? Correct, class? I multiply by s plus 3 squared, gets rid of that. Multiply by s plus 3 squared, s plus 3 squared. Everybody agree with me? Right? Y'all see what I'm doing here? Now, what I showed you, the next step is take a derivative with respect to s of both sides. Correct, class? When I take a derivative of this one with respect to s, what do I get? Taking a derivative of this. I can take the 12 out in front, right? Derivative of s is 1 over s plus 1, correct? Plus s times the derivative of 1 over s plus 1, which is going to be what? S plus 1 squared with a minus sign right here, correct? You agree with me, everyone? How many see that? Right? Now remember, I'm going to evaluate that at the pole, which was what? S is minus 3, correct, class? It's this complex pole. Does everybody see that? Now, when I take a derivative on this side with respect to s, what do I get here? Come on. A times s, derivative of that with respect to s is? A, thank you. Derivative of 18 with respect to s is?
0.
Thank you. And finally, the derivative of that with respect to s is, I'm just going to tell you one thing. You don't have to do it. When I take a derivative of this, no, there's going to be two parts. The first is going to be minus 3, can come out in front, just leave it there. Derivative of 1 over s plus 1 is minus 1 over s plus 1 squared, times the second, s plus 3 squared, right? Plus the first, which is 1 over s plus 1, times the derivative of the second, which would be 2 times s plus 3. Understand, class? Now, when you evaluate this at s equals minus 3, it goes away. Follow me on this? This will always go away when you do that. And it means when I take a derivative, a can be found by multiplying the x of s by the highest order pole, and then taking a derivative with respect to s, and whatever's left you evaluate at the pole, the higher order pole's value. Understand, class? How many do? How many remember seeing that? A lot of you do. Some of you do. That's the first method, and that's the method I generally use. And if it's a third order pole, then you would start with a third order pole. And there's permutations on this. I don't usually give third order poles for anything because it takes a little too long to work through the nitty gritty details, unless it's real simple. So that's how you do it. Now, what is this going to be? Back to this. What is A? Take a look at this. S is what? Where's the pole? Minus 3, correct, class? So at minus 3, what happens? Well, this one becomes what? Minus 1/2? That's minus 1/2. And what does this one become? Well, that's minus 3. I have what? 1 minus 3 is minus 2, correct? Squared is 4, correct, class? Then I have minus 3 over 4, where the minus sign is 3/4, isn't it, class? So this is going to be plus 3/4. And what is that going to be? 1/4, isn't it, class? So I'm going to have 1/4 for A. Now, getting back to the inverse of this. Now, I'm working through this kind of fast because I want to get at your question. So finally, for this one, I have A, which is 1/4, right?
Wouldn't it be 1/4 times 12?
Yes,
So
yes.
3.
I'm sorry, 3. Thank you, 3. My bad. You're absolutely right. So it's 3 over s plus 3. And this was 18 over s plus 3 squared. And what was this one again?
Minus 3 over
Negative 3 over s plus 1.
All right, now we go back to the time domain. That was x of s doing partial fractions. So if I'm going back, do the easy ones first. You see this one just goes as what? Class, to the time domain? Minus t u of t, correct? What about this one? Agreed, class? What about this one? All right. Now, you can look at your tables. Do you remember?
18T, E minus
Yes, you got it. Let me do this one for you. This one should stick with you because you see this one all the time. If I had e to the minus at u of t, you know from experience that this is just 1 over s plus a, correct? And then you know that if this is like my x of t, that t times x of t over here is what? Minus d ds of 1 over s plus a, correct? Right? Remember that? And what is that? That's just going to be 1 over s plus a squared. Isn't it, class? How many see this? That one you run into all the time. T times e to the minus at u of t. I'm telling you that from experience all the time. So this one is just going to be plus 18 times t e to the minus 3t u of t. And that's the inverse of that. And that's using a second order pole. Second order. We could do a third order. In the book he talks about this, and if you do the reading, you'll see it laid out in a lot more succinct way. But if you see it done with real stuff up here, with real numbers, it usually means more to you. I'm telling you that. You can read through a lot of theory, but when it's done with real numbers, going the whole 9 yards, going ahead, doing partial fractions, then bringing it back to the time domain, it should stick with you. Do you all understand what I'm doing here? Why I did what I did? Now here's the other way to do it. Tell me when everybody's got the notes down. I see people writing. This is the way that I see it more often done by students. So I'll just tell you, this is the way I see it more often. All right? Got it? Let's go back. We know what the answer is, but to get those constants, here's what happens. If I had that original function, tell me that original function again. It was s plus 3 squared, right? And s plus 1, and on top it was 12s, is that right?
Yes, sir.
All right, the way a lot of times this is done, we're going to have a over s plus 3 plus b over s plus 3 squared plus c over s plus 1. Now, here's the way most of you will probably do this on an exam, a problem like this. Y'all see you can get c very easily, right? Correct, class?
Yes.
Y'all see you can get b very easily. Do you agree, class? Because it's really just multiplying this side by s plus 3 squared and evaluating whatever's over there at s equals minus 3, right? But instead of doing the derivative to get this, what they do, most students, they get and take all these constants under a common denominator, which is this. And then they equate powers. Let me show you. So they're going to say that I have s plus 3 squared times s plus 1. That's the original common denominator, correct? Now, a, if I look at s plus 3 here, I would have to multiply top and bottom to remain as 1 over s plus 3 by s plus 1 and s plus 3. So I take a, s plus 1, s plus 3. Follow me, everybody? Plus, now b, there has an s plus 3 squareds, but I have to multiply it by s plus 1 because it's down here. So now I put b times s plus 1. And then c has to be multiplied by s plus 3 squared. Now, if you just divide out, I mean, if you take s plus 1 and s plus 3 and divide it down here, you get a over just s plus 3. Correct, class? Y'all see what I've done here? Got everything under a common denominator. And here's why it's interesting. If I look here, I have s squared times 0, don't I? Then I have 12s, and then I have plus 0 as the constant. Follow me? Now what we do is equate coefficients on both sides. So if we look over here at the highest power, by the way, we actually want the value, we've got the value of c and b just easily, right? We want the value of c, correct? I look over here for c. Let's see. C, I can take the highest power. I can have, there's an s squared that's going to be here. So I'm going to have, for s squared, I'm going to have a, it's going to be times s squared, right? Plus c times s squared. would be a term. Then there would be another coefficient for s, right? Some unknown coefficient times s, plus some unknown coefficient, which is a constant. We don't care about these. I'm just caring about the coefficient of q, because what do I know? I mean squared, pardon me. I know that the coefficient of s squared is 0 over there, correct, class? You all see that? And if it's 0, then if I know c, I know a. A is just minus c. Is that right, class? How many of y'all see this? How many did it that way back in the day? I knew it. Students hate doing derivatives. I found that out. All right, they don't care for integration, but they hate derivatives a lot of times. Well, you can do it either way. You get the same answer. It doesn't matter to me. Follow me, class? All right. Now, next, I've got a few others. And I'm about, maybe I'll take your question. And then, well, let me do one more. By the way, where's the snow supposed to, where's the southernmost point in Alabama that's supposed to get snow right now? Birmingham? I don't know, I'm just asking, because they usually have a snow line at AccuWeather. Where is it?
Birmingham's gonna get it.
But no further south?
So I think it is. I think
like
exactly where.
Birmingham's.
If you look on AccuWeather, if you don't mind doing this, AccuWeather started at Penn State, and that's where I did my undergraduate. And I remember a friend of mine was a meteorologist, and they spent a fortune of weather forecasting. Governments of the world pay a ton for this. This is not NOAA weather and stuff. This is not the generic, 5-day forecast. It's very exact. Countries pay a lot for this, especially when they're involved in military exercises and wars. And I remember him telling me how intricate it was, but it's also very, very accurate. AccuWeather's, I hope I don't get in too much trouble for this. AccuWeather overall is the most accurate forecaster that you're going to see. Does anybody use it? AccuWeather, some of you, you take a look at that and you just watch. 9 times out of 10, they nail it right perfectly. Anyway, getting back to this thing, here's the next one. Remember when we had cosine of omega naught t u of t times e to the minus at, that one. We did this one, right? And it was a plus s over a plus s squared plus omega naught squared, right? And then we did e to the minus at times sine of omega naught t u of t. And this one was just equal to what? Omega naught over a plus s squared plus omega naught squared, right? Those forms crop up all the time. Now remember, if a is 0, you default just to the cosine or the sine, right? And for cosine, it's just what? S over s squared plus omega naught squared. For sine, it's just omega naught over s squared plus omega naught squared, right? But those forms happen. The thing about it is, in order to get this form, often you have to do something called completing the square. Now, I think I told you, but let me just do this real quick. Suppose I had this. I have 12 over s squared plus 2s, all right, plus 9. And I wanted to find the inverse transform of that. Now we can do something where we actually find out where the poles of this are. If you take a look at this, I don't think that factor is exact. I hope it doesn't. If it doesn't factor exact, then what you end up getting is a complex pole. You get a real and imaginary number, and then a real and the conjugate of the imaginary number, right? Remember when you do the quadratic equation to find the roots of an equation? That's fundamentally what you do. And you can get complex numbers. That's what you get. But we don't want to use complex numbers. You can't do them in calculators. We don't want two poles that are complex conjugates of the other. What we want to do is keep it in terms of sines and cosines. Do you follow me on this one? And they're a lot easier to actually see what's going on. So when I take a look at this one, I complete the square, and listen carefully, and I'll slow down here. The way you do it is you take a look at the coefficient of s. You'll notice the number 2. Divide that by 2, which is the number 1, and put it here. So I have s plus 1 squared. Whatever that coefficient is, you divide it by 2. Got it? Now go ahead and do this and square it out. I have s squared plus 2s, don't I? So I got the s squared 2s, but now I'm left with plus 1, right?
So you need plus 8.
That's right. Then I add 8 to it. And I should have done 10 there, so I would have had 9, and then I could have said the square root of 9 would be omega naught, but I didn't. Tell you what, I'm going to do it anyway. Rotten person that I am. So it's going to be plus 9, right? Listen. Now listen. Remember, the form I want to fit here is going to be this one. Got me? Now, I already can see what A is. A is 1. I'll put it down here. So A is 1. And I can see that omega naught here is 3, right? Correct? Right? We don't have 3 up there. We got 12. Or we have 4 times omega naught. Follow me on that, class? Give me a show of hands if you do. So this is really 4 times omega naught. Now, the way you do it, whatever omega naught is, you divide it into that number, and whatever's left, you put up there. Understand? How many do? When you work these problems several times, it will become very clear, I hope. And I'm not trying to do this in a way that's super rigorous mathematical proofs. I'm trying to get the point across, because my God, you're engineers, and you don't care about the, no, I say this, and I'll probably get a letter from the math department. But what you're worried about is knowing how to apply all these techniques and get the right answer. Elegant proofs are for the mathematicians and maybe some other abstract people, but we work with hardcore stuff to make money. So that's what it is. Understand? Now, what's the inverse of this? If we want the inverse of this, what would it be? Okay, let's take a look at this. It's 4 times what? 4 times what? E to the minus, just minus t, right? Times cosine of what? Or sorry, times sine of what?
3t.
Times sine of 3t u of t. Are you with me? Now, there's a lot of things. You may see this as a factor, and I'm going to draw. I want to show you that too. By the way, we could do this one too, couldn't we, class, if we had 2 terms up top? Agreed? I just did that one for simplicity because I've got 9 minutes left, and I'm trying to get to his point. All right, don't you have a question?
Well, I mean, it was like, you did the double pole, so that was kind of a question. So.
Was there anyone, let me just show you where I'm going with this. We could do this one too. I could put that something that matches that form when we complete the square. That's obvious though, how to do it, right? Once you complete the square, you just match the form, right, class? All right, now watch. This is important. So if I had this, suppose I had this. 15s over s squared plus 2s plus 10, I'm going to use that one, over s plus 1 right here. And I wanted to find out what the inverse Laplace transform of that would be. You all see there's 2 poles you got to put down. You have to put the s plus 1 by itself, and you have to put this by itself, correct? Right? Now I'm going to show you something when you do this to save you some time. When you do this, go ahead and put this one down first. So you're going to have s squared plus 2s plus 10 here. But then put down as plus b. You're going to solve for both a and b. All right? Maybe b 0, maybe it's not. Then it's going to be plus this. Plus c over s plus 1. Understand, everyone? Listen up now. You all with me?
Yes.
Now, can you all see we can get c very easily, right? With me on this? You're going to like me for this one. Once you have c, you can put them all under a common denominator and just equate powers again. And it becomes obvious. Do you follow me in this, class? So then I could say I would multiply this by s plus 1 right here. And I'd multiply this by s squared plus 2s plus 10 here, right? And then I'd have everything under a common denominator. Then everything would be over s squared plus 2s plus 10 times s plus 1, and then you would solve by equating powers. You'll notice 15 is only the coefficient of s. 0 is the constant, and 0 is also the coefficient of s squared. So for s squared, what do I have? I have a, s squared, and I have c. So a plus c is 0. Follow me? And since you solve for c, you've got a. Got it, class? How many see this right here? And then you can go backwards and do it. How many see this? I'm trying to work in the thing. Now, I did want to work a couple problems. I'm sorry, I threw those problems at you, assuming that you do some reading, you've had this before, and it just kind of, you know, tweaked your memory so this stuff came back. But I want to do a few of these problems. That's the reason I'm trying to get through this quick. I'll do the one that you asked me about, if you can give it to me.
Yeah, it's s squared minus s plus 1 on the top, and the bottom is s plus 1 quantity squared.
S squared, go ahead.
S squared minus s plus 1.
S squared minus s
Plus 1.
plus 1 over.
S plus 1 squared. Just that whole thing. Yeah.
All right, well, first of all, I'm glad you picked that one. You see that the power on top is the same as the bottom, the highest order of s is squared. So what you do is you divide this out, and you're going to get a constant, all right? Now here's what. What is the if I have a delta function, what is the Laplace transform of it? Delta t is 1. If I had 12 delta t, it would be 12. Follow me? So that constant will be something we just put a delta function down for, all right? So let's go ahead and divide this out. First, you agree that this is equal to s squared minus s plus 1 over s squared plus 2s plus 1. I just go ahead and did the multiplication, correct, class? If you haven't done this one, I'll slow it down just a little, but I want you to make sure you see this. Everybody on this? It's real important. So now, we're going to divide denominator into numerator. So now I take s squared plus 2s plus 1 and divide it into s squared minus s plus 1. And it looks one time, right? Right? And then I go ahead and write this down below it. So I'm going to have s squared plus 2s plus 1. This is just s, right? And then I change the signs in this or subtract them, basically. So when I subtract them, what do I get? 0, right? When I subtract them, I have 2s here, correct? Minus s is going to be minus 3s, correct? And then you're going to have what? 0. So I'm left with minus 3s. So I can say that this term is actually equal to 1 plus the quantity minus 3s over s squared plus 2s plus 1. Do you all agree with that? With me? Show of hands here, right? Make sure you see this. Can you see in the back? I ask this all the time. I had one kid, he's like, I can't see anything, but I'm not in your class. That's appropriate. The back rows used to get populated by the next class coming in, but they don't seem to be that way these days. All right, let's go back now, go to the time domain with this stuff. First one, 1 goes to delta t. You'd be surprised how many people forget that. I'm not kidding about this. They really do. What about the next one? I can take the minus 3 in front. Well, let's just do this one. How do we get this one? I want to ask you something. Do you see something here that might be appropriate? Let's go ahead and do this. If I have just minus 3s by itself over this, what do we see here? S plus 1 squared, right? Right? Isn't that right? So, what? Now, if I have that, how would you do it?
Multiplying by s, isn't that like a derivative on the x and t?
Why don't we do this first? What is this going to be? If this is my x of s, what is my x of t? Think about it. Minus 3 over t e to the minus t u of t. Correct, class? Is that right?
Yeah.
All right, do the next part. Now, if that's x of t goes to x of s, if I have s x of s, what happens? Right? And there's also what? Minus x of t equals 0 plus, right? Correct, class? What is x of t minus 0 plus here? What's x of t equals 0? I mean, what is the value of this of t equals 0? 0, right? Which is just this, right? So what you can do, there's a couple ways to do it. Take a derivative of this with respect to t. Are you with me? Just take a derivative, yeah, just the derivative with that with respect to t, and that'll be the answer. And I am out of time now. I wanted to do one or two more. I'll show you more tricks to do this. There's not just one way. You can actually, if you want, for this one, if it's an S here, right? We can do a formal inverse of that if you want. I mean, we can keep working at any permutations you want of that. If you have more questions about this, I'll be in my office. I'll be happy to help you. Does that make sense today?
It's not a problem.